In this video, we are explaining star and delta connections used in three-phase power. So, single phase is what is used in your house. Generally, this is a 240 volts 50 Hz supply, sometimes even 230 Hz, available at every plug point in the house. So one of the benefits of AC is that it's readily available in the house versus DC power, which is more expensive because the DC power is portable, that's the advantage, but not readily available. Whether it is switching on a kettle, a toaster, a TV, a microwave, a lamp, or radio, it is all connected to single phase in the household. But that still leaves the problem of single phase motors. So single phase motors are not that powerful versus the three phase motors. So three phase motors are far more efficient. And so additional circuitry can be added to the single phase motor to make it self-starting. It is expensive and there are cheaper alternatives needed to be. However, in industry, the use of three-phase motors is far outweighs that of single-phase motors, as they are self-starting and they have a better efficiency and power factor. And so, the three-phase generation was born. Three-phase generation is not a magical system. It is simply three coils positioned at 180 degrees with respect to each other. There are numerous advantages to three-phase generation over single-phase generation, not only for the consumer, the people that use it, but also for the provider Eskom. A lot of these advantages may not make sense immediately, but all these aspects will be addressed in the relevant chapters and they will unfold as we work through each part. The advantages of three-phase over single-phase will be split into three categories: the generation process, the transmission and distribution process, and then the load. So remember that the load is the distribution. We can see that power can be generated by a motion of turning. For three-phase and single-phase alternators or generators of similar physical sizes, three-phase will have far more greater power that it can generate. Three-phase can supply power to single and to three-phase households using a star system. Three-phase is cheaper to generate. Three-phase requires less space. Three-phase has two connection points, namely star and delta, each with its own advantages. In three-phase, losses are limited. The star point can be used as neutral in the star generation, and three-phase supply has 3 times the power of single phase. Right, the distribution and transmission process. Power distribution happens over long distances, and so in this way the voltage is stepped up very high to be transmitted over long distances. The idea is to make that happen at high voltages and low currents. So it's transmitted at high voltage and very low currents. So lower currents means less heat. Less heat means less losses. So lower current means thinner cables then can be used and associated with cost savings. Pylons required to support these thinner cables that are high up in the air will require less metal during construction and associated cost savings. A neutral point is available when using the star system. Load distribution and phase balancing becomes very possible with three-phase. Right, so looking at a three-phase motor, notice there's the rotation, and a three-phase motor generally is 400 volts and the light bulb is 230 volts. Right, so when something is generated, the three-phase power, we can take a single phase, which is that single phase light bulb, or three phases, red, yellow and blue, which goes to our three-phase motor, three-phase induction motor. Right, three-phase motors are more efficient Three-phase motors have a higher power factor. Three-phase motors have much more starting torque. Three-phase motors do not need additional starting circuitry. For three-phase and single-phase motors of similar physical sizes, three phases will produce more power. Three-phase can be connected in star or delta. Three-phase motors have fewer moving parts, less maintenance. Three-phase motors do not use centrifugal switches like how we learned with the single-phase motors.
A healthy motor, troubleshooting a motor with a multimeter. Before testing, no matter how your motor is wired, star or delta, make sure to remove all the jumper links from the terminals. Once removed, you'll see 6 individual terminals, typically labeled U1 and U2, V1 and V2, W1 and W2. Each pair represents one complete phase winding. Any break in continuity within these pairs indicates a motor fault. Now let's check the continuity of each motor winding. Set your multimeter to low resistance range. Measure resistance across each winding. In a healthy motor, a good winding shows low resistance, and the resistance values across these windings should be approximately equal. My readings are nearly identical, so the windings are intact. If any winding shows large differences or OL, that may indicate an open circuit in that phase. Next, we'll check for shorts between windings. While windings are insulated, it's crucial to confirm. Place probes across different phases. If there's a short circuit, your multimeter will show a resistance value. An OL reading indicates no short circuit. All show OL. That's exactly what we want. No continuity means no short circuit between the windings. And here's the critical final test. Check if windings short to the motor housing. Set multimeter to high resistance range. Connect one probe to each winding and the other to the motor's ground terminal. A healthy motor shows OL for all windings, which means no continuity. If you get any resistance, the winding is shorted to ground. If the windings are balanced and there's no short to the housing, your motor is electrically healthy. If not, it may need rewinding or replacement.
To summarize, most of the above simply means smaller machines are required in three-phase motors. Less materials are also required to manufacture them. They're cheaper to produce and to maintain. Shorter manufacturing times, easy to install, and longer lasting than single phase. They also produce more power than the single phase motors. Those are more enough reasons to go with three-phase system. Right, so here we're looking at the waveform of single and three-phase systems. So the single phase generation, very basically, a single phase can be generated by rotating a conductor loop of wire through a magnetic field. Notice that the rotation is anti-clockwise. And then we have north and south field poles on the side of this loop. So when generating, it forms a sine wave. So notice we're starting at 0 and we are moving anti-clockwise. Okay, anti-clockwise, and then it forms what we call the sine wave. Three-phase generation. As mentioned before, there's no magic involved in three-phase generation. It's simply 3 coils placed at 120 degrees with respect to each other. They are usually referred to as red, yellow, and blue, or simply as L1, L2, and L3. So with three-phase, it 120 degrees separation from each other. Right, so notice here with three-phase, they are placed 120 degrees apart from each other. So the yellow phase follows the red phase exactly, except it lags 120 degrees with respect to the red phase. The blue phase follows the red phase exactly, except it lags 140 with respect to the red phase. So do note, you need to learn how to draw this for exams. So here are the waveforms of a three-phase system, as in the textbook. Do learn how to draw this exactly how it is for exam purposes. Right, so notice that this phasor diagram of a three-phase system. Here we are showing how it is connected in star connection. The EMF's voltages generated in each phase will be 120 degrees out of phase with each other. This means that the voltage in red, yellow, and blue phases would be represented as follows. So this is 120 degrees apart in a three-phase star-connected system. Three-phase systems, star versus delta. There are three voltages generated, one in each phase. The idea is not to use them as three individual single-phase voltage, but rather to combine them in specific ways to form a three-phase system. There are two ways of connecting the endpoints of the three coils together. They are known as the star and the delta connections. This can be represented by means of a schematic or diagrammatic representations. Schematic: this is a sketch without indication of components. It's making the use of lines only, while the diagrammatic sketch is with components included, is almost the way would be drawn in a circuit diagram. So in the sketch, we are comparing diagrammatic on the left versus schematic on the right. Do learn how to draw both these sketches and know when to draw which one. Please indicate the neutral at the center of the star system. Also include all labels in the diagram as L1, L2 and L3 and the neutral. Very important to do this. Here now we have a delta connection. So in a delta connection, the end of phase 1 will go to the beginning of phase 2. In other words, this is like a series connection. So notice diagrammatic is on the left, including the components. Diagram on the right is not diagrammatic, it is schematic. So notice the words diagrammatic on the left, schematic on the right. Schematics do not have the components. Since all alternators, generators and motors use windings of copper wire, each phase would have the resistance of that copper as well as a certain inductance. The reason for the inductance is that the wires of each phase are turned around a core to form a coil. In effect, that is an inductor. So calculations for star connections. So remember, with the star connection, we have two voltages. We have a voltage between live and neutral, and if you test this with a multimeter, it would be around 230 V in South Africa. And if you go across the two lives, between L1 and L2 for example, or between L1 and L3 for example, or between L2 and L3, you will get about 400 volts or slightly less than that in some cases.
Onto volts. We're going to wait for it to power up. All right, now this is a three-phase contactor. It's got 3 poles of power. It's got 1, 2, and 3. To check three-phase power, what we want to do is take our meter leads and go on the first and second leg, and we're reading 207. Then we want to jump across to the first and the third, 205.8, and then we want to go to the second and the third, 206.5. So that is how you check three-phase power. Make sure your meter leads are in, consider gloves.
Now we will place the black probe on neutral, and then we'll go to L1. We will get about 230 volts. Then we'll keep the black probe on neutral and we'll move to L2. We will get the same voltage, and then we'll move the other probe, the red probe, to L3. We will still keep the black probe on neutral. Notice that the voltage will be equal between L1 and neutral, L2 and neutral, and L3 and neutral. This is measuring of single phase. Right, calculations with delta connection. So here we only have one voltage. So the phase voltage is equal to the line voltage. So if we go across L1, L2 or L1, L3, whatever the case, we will get only one voltage, and that voltage will be around also 400 volts or slightly less. Right? We note that with calculations there's a root 3 involved. Okay, root 3. with all these three-phase calculations. So please remember, when calculating, use root 3. Also understand the values. When you have kW, it is true power. When you have kVA, it is apparent power. Do read these notes on the screen, just for some clarity. Right, moving on, we got something called active power. Now, active power is also the real or the true power. So this is the actual power that the person would pay for, the true power. So power is equal to root 3 IL VL cos theta. What is cos theta? Cos theta is the power factor. What is theta? Theta is only the phase angle. So if you get a decimal value in an exam like 0,8, 0,9, you will substitute that whole value as cos theta, not as the phase angle. If you are given degrees, then that is theta. So please note, if you get a value that is in a decimal form, listen closely, 0,75, 0,8, 0,9, you will substitute that value for the whole of cos theta. So where you see cos theta, take it out and place 0,8, 0,9, whatever the case is. Apparent power is exactly the same formula, but notice there is no cos theta. So when you see cos theta, you will know that that is the true power. When there is no cos theta, it is the apparent power. Also note that the units are different. kW for true power, apparent power will be kVA. Notice here, reactive power is sine theta. So to find the reactive power, this means you will need to find the phase angle first from cos theta. For example, if cos theta equals to 0,8, I will solve for theta. After solving for theta, I will then substitute it into theta for the reactive power. In this way, I can now calculate the reactive power. Do note that the reactive power includes a R after the unit of apparent power. So apparent power is kVA. Reactive power is kVA or reactive. Remember, there are losses. Whenever we convert from one form of energy into another, there are bound to be certain losses. No machine is perfect, and therefore it cannot work 100% efficient, as there are also always certain losses. Some are considered electrical losses, while others are called mechanical losses. So in an exam, they will ask, what are the electrical losses and what are mechanical losses? And then you will have to list them. The basic losses can be categorized as follows: copper losses, iron losses, core losses, friction losses, windage losses. Which two of these losses are mechanical? It is the last two, frictional losses and windage losses. So windage losses is from the word wind. So as something moves, you're going to get something called rotational loss, which is the windage losses. Copper losses. These are basically due to the heat. Okay, so the resistance of the copper wire used in loops of wire, they make up the windings of a generator. Any current that flows will experience a resistance that will create heat. Copper losses is exactly heat losses. Then we have the iron or core losses. Now the iron and core losses are linked directly to circulating heat currents called eddy currents, right? The core of a generator armature is made up of soft iron, which is a conducting material with desirable magnetic characteristics. Any conductor will have currents induced in it, and it is rotated in a magnetic field. The currents that are induced in the generator armature core are called eddy currents. The power dissipated in the form of heat as a result of eddy currents is considered a loss. Now we got the mechanical losses. The mechanical losses are frictional losses. The full weight of rotating parts is carried by the bearings, so the bearings have friction. This will make the motor rotate. However, there is some friction due to these bearings. Okay, it's called frictional losses, and these bearings also heat up somewhat. Now we're looking at windage losses. The alternator generator has fan blades on the rotor that blow air through over the alternator to keep it cool. The losses due to forced air movements are called winding losses. So as the motor spins, there's a fan. The fan is used to keep the motor cool, but this we also get some resistance due to the rotation as the motor is rotating and the fan is blowing wind. We call that the windage losses. So remember that the frictional losses, I'm sure you understand what friction means. So although these bearings make it easy to rotate and reduce friction to a large extent, they still experience some form of friction. This friction results in unwanted heat. So these are mechanical losses. And we can calculate efficiency by using the formula shown on the screen. Advantages of power factor correction. So when your system is running very efficiently, and if you can get a power factor of 1, which is called unity power factor, in other words, cos theta is equal to 1. If cos theta is 0.9, this means you're running at 90%. If you have 1, this means you're running at 100%. I hope that makes sense. Advantages of power factor correction. For the consumer will use less current drawn from the supply. This will result in cost savings drawn because he's using less current. Less heat is generated. Maintenance will be reduced because the motors are running cooler. He will have a longer lifespan of his motor and a longer lifespan of load. For the supplier, what does this mean? If power factor correction is done properly, this means he will use thinner wires to supply his power. So there's a saving already if you're using thinner wires. This will lead to a reduced cost as a result of these thinner cables. The supplier's machines, they are not under so much stress to produce electricity that is wasted. So the machines that are generating the power, if power factor correction is done correctly, these machines will not be working too hard to produce the electricity. So there's less electricity being wasted. This means it's more efficient and less maintenance. And there is therefore a longer lifespan because the machine is not working as hard. Right, then we have something called watt meters. So the purpose of a watt meter. So the purpose of a watt meter, remember that V times I is equal to watts. So if we can measure the current and the voltage to a load, this means we are definitely calculating the wattage. So power can be measured by connecting a voltmeter in parallel and an ammeter in series. And by recording the two values, multiplying them together, we can then get the true power that is consumed, right? But this method of measuring doesn't take into consideration the power factor. Therefore, our answer we get here is going to be apparent power. So a watt meter is connected like this with the series coil measuring the current and the parallel coil measuring the voltage, and this is how a watt meter is connected, like this on the screen. Right, these are the types of watt meters. Okay, this is what they look like. They have a moving coil and it's calibrated and you can read off it. So you have analog types, which are very old, which are hardly used, and we have the digital types, which are very common now. So the watt meter is an instrument for measuring electric power that's consumed. Okay, it essentially accumulates or averages readings. Electronic watt meters are used for direct small power measurements or for power measurements at frequencies beyond the range of electro-dynamo meters type instruments. It basically samples the current and the voltage thousands of times a second for each sample. The voltage is multiplied by the current at the same instant. The average taken over at least one cycle is the real power. Now we have something called a kilowatt hour meter. We find these on the side of our house. Now there are modern ones nowadays that are electronic, but if you go to your house on the side, you will find these meters. A typical example of a kilowatt hour meter as well is our prepaid system that is digital, but on the side of your house you actually have a mechanical one like this. And what this does, it tells us how much electricity was used over a period of time, and so we get billed according to the kilowatt hour meter. So how it works, we have two coils in the meter with a disc that spins, and as this disc spins, the numbers keep turning up. Okay, and so you can look at the picture here on the left of all the labels that are there to understand it. So there's a current coil and it has a potential coil. So the potential coil measures the voltage, the current coil measures the current. And so remember we said that VI is equal to watts, and then it has this permanent magnetic disc that spins, but it also breaks as the power goes up and down as it's being used. So the volt coil of the watt meter is connected in parallel to the supply, because voltmeters are connected in parallel. It consists of a coil with many turns of fine wire and a laminated coil. This coil has a high resistance to prevent as little current as possible flowing through, so it does not interfere with the operation of the circuit. The voltage coil is designed to produce an air gap magnetic flux which is proportional to the applied voltage. The current coil, however, is connected in series with the live wires. Ammeters are also connected in series. It consists of a coil of a few thick turns and a laminated core assembly. This coil must have a low resistance to not interfere with the operation of the circuit. The full load current flows through the coil. The current coil assembly must produce an air gap magnetic flux, which is proportional to the current drawn by the load. Now we're looking at power factor meters. So power factor meters look like this, and when they get closer to 1, this means they are running at unity power factor. So cos theta is equal to the true power over the apparent power. So in other words, power actual over power apparent, and this will give us cos theta. Right, so remember that the purpose of the neutral for unbalanced loads is that the neutral takes up the unbalance, right? So these are the two ways of how we can connect our watt meter in a series system like the Delta system. We will connect our watt meters across P1, P2 and P3 as seen there. So using 3 watt meters, the easiest way to get the total power consumed is to add up P1, P2 and P3. So this is using 3 watt meters. So if the question says draw a diagram showing how 3 watt meters are connected to the system, it would be like this, okay, to a 3-phase system. And this is what we call the 3 watt meter method. So here we can see we have 3 digital watt meters, and they're used to measure the power in unbalanced loads. Unbalanced means that every phase is not having the same amount of power drawn. So then we add up the 3 numbers, and that will give us our total power consumed. Okay, so this is what we call the 3 watt meter method. All you do, you add up the 3 values. Don't forget to start with a formula. This is now what we call the 2 watt meter method, and notice that the neutral of both the watt meters are connected to the center phase, which is L2, and the other side would be connected to the L1. Okay, so if that makes sense to you, so on the watt meter we got 2 wires. One wire goes to L1, the other one to neutral. The other watt meter goes to L3 and the other side to neutral. And this is how we connect the 2 watt meter method. The main advantages of the 2 watt meter method are the total power can be measured in a balanced or an unbalanced load. The total power can be measured in star or delta systems. The terminal is easy accessible, as only the live wires to the system are required to do the connections. The power factor can be determined. Okay? Cannot determine if the power factor is leading or lagging. The total power in this case simply calculated by adding the readings of the 2 meters together. So power total equals to power 1 plus power 2. Okay, one of the main advantages of the 2 watt meter method is that you can use 2 watt meters instead of 3 watt meters. That is definitely an advantage. The disadvantage, you cannot determine if the power factor is leading or lagging. This is the formula that you would use to find out the phase angle using the 2 watt meter method. And when you have that angle, you can then substitute it into cos theta to find the power factor. Don't forget that the formula is √3 on the outside. Subtract the 2 readings on the top. Use the exact same 2 readings at the bottom in the denominator and add them. So here we are using this formula to find the phase angle and then cos theta to find the power factor. You would use this formula when there are 2 watt meters. This is what we call a 3-phase transformer. So 3-phase transformers, the principle of operation and connections of 3-phase transformers. Before 3-phase transformers are discussed, it is important to know where they fit into the national distribution of power in South Africa. On one side there is a provider, the generator, which is Eskom, and they generate 3-phase electricity. And on the other side are users or consumers, and many of them use 3-phase machines. So the consumer uses the distributed power. He would use 3-phase machines. Getting the generated power from the provider to the consumer is where the 3-phase transformer fits in. So it's used to step up, about stepping up the voltage and stepping down the voltage. So with this system, the power is generated at Eskom at 22 kilovolts. It is then stepped up. So we step up the voltage to the voltages as seen on the screen, and then we step down the voltages when we get very close to the consumer. And those are the voltages that can be seen there at the substation, right? The substation that is very close to the consumer, and then a sub-transmission customer, 22 kilovolts, the primary customer, 11 kilovolts, and then right towards the last points where it's by the consumer, 380 volts, 400 volts plus minus 230 volts. Okay, and this is what we call the distribution process of getting it to the customer.